Welcome everybody to the SPREE seminar. So today we have Prof. Hartmut Nussbaumer, who is actually currently a visiting professor at UNSW in my group. And Prof. Hartmut Nussbaumer studied physics and completed his PhD in 1996. So that's quite a while ago. And since 1991, he's been working in photovoltaics. And actually, that will be very obvious from his presentation, because he will present a lot of his learnings from this long time in photovoltaics. So he actually had a research stay at in the US at AT&T Bell Labs, so one of the most famous labs in the world. And then he moved back to Europe, Eurosolari he worked, where he held, and subsequently he also held leading positions in the PV industry, and that's actually how we met. So at Sunways Rena, as I was one of their clients when I worked in Singapore, and where he worked in management, but also in research and development. As managing director of Sunways production GmbH, he was responsible for installing a solar cell manufacturing site on a greenfield in Germany. So also a lot of manufacturing experience. So, but he left industry. Was it 10 years ago? Or?
Yep.
Yeah, 10 years ago.
10 years ago. Yeah.
And now he's working as a professor at the Zurich University of Applied Science, heading the research group on photovoltaics at the Institute of Energy Systems and Fluid Engineering. We're very much looking forward to your talk, Hartmut.
Yeah. Thank you so much, Bram, for the kind introduction. Good afternoon, ladies and gentlemen. I'm very happy to give a presentation here at the University of New South Wales. It's a great honor to me, I have to say, at this very famous university. So the title of my talk is Drivers for Progress in Photovoltaics, based on levelized cost of energy simulations in the past, present and future. So the objective of this work is to look, is it possible to predict future developments on the basis of analysis of levelized cost of energy? And I start from a retro perspective, and then I take a look into the future. For this, you see my outline. I divided the time into 4 different periods. The first period was this in the 90s, when I was starting my career in photovoltaics also. That was the time of the beginning of industrialization. And then this next decade in 2000, starting from 2000 to 2010, there was this beginning of mass production, later on followed by a period which I, let's say, name mass production and technology maturity. And the question is, of course, what comes next? Huh? Is it a disruptive change, or what we will see, or yeah, we will discuss it. So the levelized cost of energy, how I calculated is I'm using just the standard formula, where you sum up all the costs of your photovoltaic system during the lifetime, divided by the total energy yield over the lifetime of the system. And the yearly cost in the future, they are discounted by an interest rate, as well as the energy yields in the future are also discounted by an interest rate that comes from the thinking that the electricity has a kind of monetary value, which is discounted in the future. So I would like to say, to mention that my intention here is to use this tool to predict trends over longer periods. So it's not the intention to predict the most precise levelized cost of energy for a certain time, for a certain location or so. That is not my objective here. For this reason, I took some assumptions. I take a reference system, 1 kilowatt peak size, just for reference, location Central Europe, Switzerland, with a yearly in-plane irradiation of 1,346 kilowatt hours per meter square, giving a specific energy yield of 1,091 kilowatt hours per kilowatt peak, which relates to a south-facing modules in central Switzerland. Then I differentiated it between area and non-area related costs. So in order to reduce the cost when the efficiency is increasing. So if the efficiency of the modules increase, I need less area, less subconstruction and so on. And this is shown in this formula here I've used. Just an example, if I would use, let's say, have a sister efficiency of 16% and I would increase it to 32%, that will decrease the area related cost by 50%. Yeah. So what I also included in my calculation is a cost for the area itself, which is most of the time neglected. I have invested myself in PV systems, and I can tell you it's cost a lot of money to get a roof, a foreign roof, for using it as a PV for PV system. So also for ground mounted, you need the land and the land cost, and this is getting more and more substantial, this part. And in addition, I introduced a linear degradation in my calculation. So the reducing the energy yield year by year by a constant value relative to the beginning starting value. So these are the framework. So if we look at the first period, I derived the cost for the modules from this well-known graph where you see the average module sales prices as a function of the cumulative PV module shipments. This graph is normally used to show the learning rate, which is around 24%. And you can see for this time in the 90s, the module prices were around $10 per watt peak. So totally different to what we have now. The total annual production at that time was 225 megawatt for crystalline silicon, representing about 70% of the market. And the biggest players were like Siemens, Kyocera, BP Solarex, and so on. They're all around 30 megawatt at the end of this time period. So I myself was working at Eurosolare, one of the biggest player at that time, and was like 6 megawatt per year output. So just to get a feeling, it's a total different story. And then I wanted to see what kind of system costs we had at that time. I found a publication on that. So, of course, during this decade there is a huge variation in the price, but I took like an average $15 per watt peak, taking into account this $10 per watt peak for the module. So that would represent like 75% for the module and 25% for the balance of system for the rest of the system. Okay, now looking at the levelized cost of energy in US dollar per kilowatt hour as a function of the efficiency, I just made a very rough assumption. I said, okay, if there would be a technology like thin film reducing the module cost in US dollar per watt peak by 50%, what would that look like? And you can see, boo, yeah, it's a huge difference. Yeah? So what makes us clear that at that time the whole focus was just reducing US dollar per watt peak. There was, I would say, barely no one thinking about LCOE at that time. It was just what is the watt peak price of your model. So that was very important at that time, and the area related costs were close to negligible. They were really a small part. So a thin film technology reducing the price by 50% in US dollar per watt peak, no matter what efficiency, I would say, it would be a breakthrough at that time. Module lifetime and degradation, that was not very on the focus at that time of customers. If we just look back, what were the technology at that time? We had cell sizes of 10 times 10 centimeter square, efficiencies 13 to 16%, There, of course, there are exceptions. I will make a comment later on that. And even we at the beginning, in my first production site in Constance, we used silver paste at the backside, fully silver paste. It's unbelievable, yeah? And we changed it to aluminum backside, so the standard aluminum BSF. And at Oro Solari, for instance, they used titanium dioxide as an unreflective coating, not silicon nitride. Huh? So they changed it at that time, at the end of the 90s. And then for the amorphous silicon technology, that was still far below 10%. So that was the situation. The major focus was US dollar per watt peak needs to be decreased. That was the main goal. So we have two possibilities: cost reduction or enhancement of the power output. Increasing efficiency respectively. Yeah? So what were the topics then? There was a huge effort in the 90s for these kind of ribbon technologies. No one remembers it anymore. It's clear we make monocrystalline silicon ribbons. Huh? Nobody talks about ribbons anymore. But that was a huge thing at that time, because substituting the costly wafer with a ribbon would drastically reduce the cost, but there was all these kind of technology, AFG, dendritic web, and all kind of things. And the challenge was always material quality, yield, and at the end, as we know, none of these technologies survived. The last approach was the technology from 1366, which I was in contact with them, but even they disappeared with this kind of approach. Just also from what was technology-wise, there was this change, as I already mentioned, from titanium dioxide to silicon nitride. Hydrogen passivation was a big step. There was this discussion: direct plasma, remote plasma, what is better, and so on. The fight between Centrotherm and Rosenrau and so on, and aluminum back surface field was optimized with the pastes, and there were always some pastes were better than the others. And I think a big step towards multicrystalline silicon was the availability of a texturing process based on acidic texturing. That was a real push for the multicrystalline technology. Even in the 90s, there were already advanced technologies like the buried contact solar cell invented by Stuart Wenham and Martin Green in the 80s here at the University of New South Wales. Great technology. They even used copper contacts at that time, and the modules were performed great in the field. They used a heavy diffusion for these buried contacts in order to prevent the diffusion of copper into the silicon, and also LPCVD anti-reflective coating, which resulted in production then in efficiencies above 18%. It was produced by BP Solar and BP SolarX later on with the Saturn solar cell. Very nice thing. Then coming to the next decade, there was again a huge drop in the levelized cost of energy and in the module price from $7 US to below $1 per watt peak. For my calculations, I used then a price for the crystalline silicon system from 4,000 to 5,000 US dollars, and for thin film 3,000. So I really made a big step again for the thin film to see what that means. I used for the annual cost 1% of the total investment costs, and an interest rate of 4%, and a yearly degradation of 1%. So if we look what comes out here, you see again the levelized cost of energy as a function of the efficiency. First of all, let's have a look at the thin film, mainly here amorphous silicon technology. And you can see here, using a 20 years lifetime, there is really a huge gap if you can really produce these thin film technologies to much lower cost, which is the idea behind it. However, here, interestingly, if I'm using only 10 years lifetime, doesn't work. It's a much higher, the levelized cost explode, because you see, we go from this curve to that curve. And interestingly, if you could look at the data sheets of these technologies, of amorphous silicon, in that time, they didn't give a guarantee of 20 years. The guarantee was only 10 years. So, in principle, they faced this curve here. But nevertheless, that was not so much in the mind of the people. They really were thinking, wow, that's a huge opportunity to go there, to really realize these lower costs compared to crystalline silicon. And that was the start of also for the hype in amorphous silicon with Oerlikon and Applied Materials, and of course also the cadmium telluride technology for first solar. What we also see here, if I'm using higher cost for sun power technology with higher efficiency, you see it's realizes in higher LCOE values, and these kind of products were mainly used were used for residential market or high quality niche markets where you needed an high efficiency, not for the let's say utility scale market. So what in this phase in 2000 to 2010 we had a very important thing happened in 2000. The Renewable Energy Source Act in Germany passed through, and that gave the customer a favorable loans, but very important fixed feed-in tariffs for 20 years. Yeah? So that came first to the minds people. Oh, 20 years! I have a time span of 20 years where my system should work. Yeah? So that was the start of this 20 years discussion. I think in 2000. So it gave a strong market push. And also then the module lifetime came into the discussion. What is the lifetime of the module? And this push also resulted in production sites in Europe, mainly in Germany, Q-Cells, Solar World. It was a huge hype at that time, in the time period. They were the market leaders, world market leaders at that time, and you know the story how it ends. So the cell size changed from 12.5 times 12.5 to the 15.6 times 15.6. That was for a long time a standard. And the efficiencies were around 16 up to the high end 22.4% production of sun power in 2007, mass production of this kind of IBC back contacted solar cell. And then in 2004 you see here this green part here in the production. In 2004 there started the let's say the huge production hype in China. Yeah? I was also then later on together with Centrotherm and Rena, and it was a huge hype for the machine builders. They just sold the technology, complete turnkey lines to China in a tremendous way. And that at the end, China took over the lead, you can say, in production capacities. And thin film technologies, as I already mentioned, there was first solar with cadmium telluride and this hype with amorphous silicon with Oerlikon and Applied Materials. So what have been the technology trends there? I think the main reduction of this US dollar per watt peak was due to the increased productivity. It was mainly the aluminum back surface field solar cell standard, and there had been some approaches to increase the efficiency. I remember very well the selective emitters, all kinds of different selective emitters. This was the one I show here, the edge-back emitter from Schmid, but there were lots of technologies. But at the end, I would say the most important thing was the improvement of the pastes and the fine line printing. This really pushed the technology in this time enormously. So that was the main thing. There was also laser opening of unreflective coating with plating developed at RENA. Really, we ended up at also having modules in the whole cycle was passed through. The technology was ready. No one took it over. So it's already since that. What we have also observed in this decade was for the first time an increase of the price while adding capacity. That was due to a silicon feedstock shortage at that time. And it was already foreseen in the 90s. Here's a paper in the 90s showing up there is a silicon feedstock deficit which is growing. No one did anything. So we can think about what kind of alarm brings it to us when we look at the silver consumption in a terawatt scenario, which we will face in the future. Then hopefully we will be more present at this time and not seeing these price increases. So summing up, to summarize this decade, the driver was not a disruptive technology change at that time of decreasing the price of the modules. It was a continuous improvement and economy of scale which resulted in this significant reduction of the module prices. And we have seen this silicon shortage which resulted then in a module price increase and slowed down the market development. So coming to the third period of time, this mass production and technology maturity, which is 2010 in my view then until now. So there is again a huge price drop in modules. You see we are now in this period below $1 per watt peak, and currently the market price is 11 cents per watt peak for wholesale sailors, of course a little bit depending on technology, which is phenomenal. It's really amazing. Just to get an idea what that means in system costs, I have here a publication from Fraunhofer ISE from the year 2021, and for a large rooftop they say an average price of 1,120 euro per kilowatt peak, and I took, as we are now in 2024, I took $750 per kilowatt peak, which relates a bit to this low value in 2001 for a large rooftop. But it is not my intention to predict the most precise LCOE anyway. So again, I've used 1% yearly cost of the investment cost and a low interest rate of only 1%. So showing now I show the levelized cost of energy as a function of efficiency again. Let's draw our attention first to this section in 2010. So assuming a 40% lower cost for the thin film, you see, even if you have 40% lower cost for the thin film, you need a kind of threshold efficiency to compete with crystalline silicon. You see, it's about 11% efficiency. If you're not above 11%, you cannot compete with crystalline silicon. And it really was like this. They fight it. There was a huge thing. This with applied materials and Oerlikon, and they pushed and they invested a lot of money in getting over this threshold of 11-12% for the module efficiency. But they were too slow. And then the window of opportunity collapsed, and crystalline silicon, with large economy of scale, went down, price down, and amorphous silicon disappeared, except of niche markets. So that was the story, and you can easily see it here. It's just, if this is going down, and then there's no opportunity anymore for amorphous silicon. And now if I go to 2024 crystalline silicon, I just to see what happens here. I have two lines with 20-year lifetime, interest rate 4%, 1%, showing that interest rate is a significant factor. Yeah? But more important here, this orange dotted line is a 20-year lifetime 0.4% degradation as a function of the efficiency. And what you can see here, if you compare it with the tandem technology, which is in all minds, we need tandems and so on. First of all, what is important? We are here in a range of 5 cents per kilowatt hour, which is for most of the areas in the world below grid parity anyway. So this little bit here, okay, yeah, it has an effect, but if I add some cost, like 50% higher cost for the tandem module, we are just at the same level. And even if I say it's the same US price per watt peak, yes, I just continue with this line, you see, okay, there's a little bit of improvement of the LCOE, but it's not a game changer. Yeah? So, but if we look at the degradation, if these new devices would have a higher degradation rates, then they are not competitive anymore. Huh? So this is quite interesting. And then I went more in detail with this. So I compare here crystalline silicon, all of them 20 years lifetime, interest rate all 1%. 23% efficient crystalline silicon and 50% higher cost for the tandem. You see, they have similar LCOEs. There's no benefit. And so, yet now it's very interesting, I think. Even if I say that they, thanks to Nathan, the discussion with Nathan here in the auditorium, even if we think that the price per area remains constant, so if I increase the efficiency in the module, so I need less area in the module, so I could decrease the price even, so I could decrease in this scenario the price in US dollar per watt peak for the tandem. Yeah? In this scenario, which I think is a hard challenge. And this will never happen. It's the same price. So it means that you do not add any cost. So you see, okay, even in this, let's say, wonderful scenario for tandems, a miracle scenario, you could say, you see an effect, of course, in LCOE because you have higher efficiency. Clear. You go from 23 to 32%. Yeah, okay, you have an effect. But now think about it would have a 2% degradation rate instead of 0.4, and the advantage is gone. Just a little bit of more degradation, advantage is gone in LCOE. And this is just for 20 years lifetime. It will be even worse for 30 years. So, and then I even zoomed it in again and said, okay, how could we, what can we extract? So you see here, I assume all technologies having the same US dollar per watt peak. So the crystalline silicon and the tandems have the same US, this is an assumption. And then what is interesting here, if you compare a 22% module crystalline silicon with a 32% tandem, yeah, and this is interestingly gives a difference in 0.5 cent per kilowatt hour. Keep this in mind. So this is for instance for 1% here. This is 0.5 cent per kilowatt hour, and this interestingly 1% degradation here gives the same 0.5 cent per kilowatt hour. So according to my calculations, what I did, 10% efficiency gain absolute can be lost by a 1% plus in degradation. So think about it. It's amazing, huh? For me, the tandem technology can only be competitive when achieving similar low degradation rates to compare to the crystalline silicon technology. Of course, there is a kind of window, you can say. An ETA increase and an efficiency increase of about 6% would tolerate a 0.7% higher degradation. But it's not so much, I think. So there are, of course, other studies from Peters et al. In 2021. In 2021, he calculated a correspondence of 5.2% efficiency to 1% degradation. So from 2001 to now, we're getting even more much more sensitive to degradation because the prices are much lower. There was this paper from Nathan Zhang here in the auditorium et al. And he calculated what is the potential cost you can add in order to be at the same level of LCOE. But I think since that already changed because the prices dropped dramatically, I think the situation is getting more difficult for tandems at the moment. And just for the sake of completeness here, on the right side, a study, a levelized cost of LCOE analysis from Fraunhofer ISE, showing the sensitivity. And interestingly, here the lifetime is has the second highest sensitivity, but they didn't study degradation, interestingly. There was no sensitivity analysis on degradation yet. So, what is the status now? If I take a technology roadmap of one tier one player now, like Jinko, I think they are all similar. You can take each technology roadmap of the tier ones. They are very similar, except that the one like Huasang, they have heterojunctions, but the rest, like they have mostly TOPCon, and then they go to tandems. You see here. We are in 2024, and then the next there will be a full passivated TOPCon technology, and then of course the next step is tandem because there's no room for improvement anymore. Question is maybe they should better have a roadmap for lowering degradation and enhancing lifetime instead of thinking about the tandem because tandems, so we can discuss later. So the question is, what comes next? So we are really, with the crystalline single junction technology has really reached the full potential. In some regions, PV is the cheapest source of electricity. Degradation we have seen in lifetime of the models is of high sensitivity for LCOE. Subconstruction, labor cost for installation and cost for area represent a more and more increasing share of the cost. And there is one aspect which I think is very important, is the time-dependent value of energy during the day and seasonal dependence. You see here an example, energy charts, Fraunhofer ISE in Germany. The yellow part is the solar power of the total power. It's more than it's the largest share. So if this is doubling, you have at midday in the summer you have an overcapacity of electricity, so that will have an impact on the price, quite sure. It already started. So I think we have to think about that one. So what comes next? One direction, obvious, we have seen the roadmaps, everyone goes to higher efficiencies. Tandems is on the road. Multi-junction solar cells, up and down conversion, these are the possibilities to increase the efficiency, which is good, I think. The target is, of course, lowering LCOE by increasing the energy output, efficiency respectively, or even theoretically, which I don't believe, that you can reduce, or not believe at the moment, that you can reduce the US dollar per watt peak with these tandem technologies. I think this is still a big challenge. If you think about how long did it take to have mass production of crystalline silicon, all the machineries and all these kind of things to be run with this extremely high yield. You have always to think about, if you make a new technology, you need yields above 99%. It is really a big challenge. So and the important thing is, and LCOE is lowered only if you have the same long-term stability, lifetime, low degradation rates, and otherwise it will not be bankable. So how long will that take? Yeah? I would not buy such a system to put it on my house at the moment, because you never know. 10 years from now, so this is one direction. Then I think we face this avoidance of shortages like silver upcoming. I think there are opportunities there. Plating is developed. Copper pastes are technologies are coming. This is one thing. Then I think really research on long-term stability and degradation to understand the mechanisms of the latest products like TOPCon and heterojunction. This is extremely important. Think about what will happen now if in 10-15 years the degradation rate will be 5% or something. We wouldn't foresee it. It will be a disaster, a complete disaster. The whole LCOE will be, the whole business cases would be gone. It will be terrible. So I think it's very important to look at this. Then increasing the energy yield per ground of roof of air per ground or roof area, I think is a very important topic. Not maybe so much in Australia because you have lots of space, but in Switzerland it's really a big topic. Yeah? You have certain amount of roofs and not so much. There are absolutely practically no ground-mounted systems in Switzerland. It's because they say we don't have the space for it. They just put now some PV systems in the Alps. That's another story. But I think the challenge is here looking at what can we get out of the given area. This is important. Then multiple use of land and building, for instance, PV and green roof, Agri-Photovoltaics, building integrated photovoltaics. These are important topics in the future from my point of view. And it's already addressed producing energy when there is a lack of energy and controlling the power output over the day, like with using tracking systems. I think this is also an important topic. The highlighted, the marked topics I will now go into and talk about a little bit results or topics from my research at the University of Zurich. First, if we want to increase the energy yield per ground area, the typical setup of a roof system is like having an east-west oriented system, low tilt angle, ground cover ratio maximized close to 100%. And the question is there a way to further increase the energy yield per area? You first think, how could it be? Yeah? Because it's completely covered. This cannot get more out of it. But there are some chances. Yeah? We are currently investigating about simple horizontal axis tracking systems with very high ground cover ratios, like 90% or even higher than 90%, just that they really are in contact, which makes the first thought no sense, because if they contact, then you tilt them, you immediately get self-shading. But we will see what comes out. And another thing is using reflecting elements in between, like for instance vertically installed bifacial modules. What can that help for? Is that something we should think about? And the second one is an idea which came up recently from us, which is not published yet. It will be published hopefully if we get it granted at the EU PVSec, to use dynamic reflectors. The idea is just to have a reflecting wall which you can weather dependent use or not, If the weather is good, you put up your wall and increase just the irradiance. It's very simple. This is not, using these reflectors is not an idea from us, but using as dynamically, this is maybe something new. So coming back to the first topic, horizontal axis tracking on roofs. We just made a simulation, power simulation, using a large field and using bifacial modules on the tracking system. And what we've done, we simulated a tilt angle of only 10 degrees. Only 10 degrees, and making a kind of flip-flop system, plus 10 degrees, minus 10 degrees. That's all. Is there an effect? You see, there is an effect. It's small, but it's there. You can see if you compare the lines. I think maybe it's not a very good plot here, but to sum in a summary, what comes out, if you have a ground cover ratio of 100% and you compare this flip-flop with this 10 east-west orientated system, it gives an increase by 11.5%. But now you have to think about it, you're using bifacial modules, and you put the bifacial modules on a specific height. And then you have to think about what is the benefit of the bifaciality compared to the east-west reference. So taking this into the account, at the end is that there is a gain potential according to the simulation of 5%. You think 5%, not a lot, but 5% is something. So if you have 5% more energy yield, we can think about what does this relate into potential investment costs, so that we can realize this kind of system. And there are other benefits if you have this kind of simple tracking system, because you can think about, in the winter you can just flip it, and then you get rid of the snow, for instance. In Switzerland is important. In January there is nearly no outcome of the PV systems because they are all covered with snow. And there's a second thing, if you put them, you can flip them, you can make the maintenance also of your models. You can pack them maybe even closer together. And there's all other kind of things which can be beneficial in this kind of new technology. So the second thing we have looked at are these reflecting ground sculpting things. There was an idea which was also published from Kahn et al. And he published that using these kind of elements in between vertically bifacial modules would give an higher annual energy yield per area, even compared to monocrystalline south-oriented ones. But he did some tricks, I would say, which are okay. I will explain. First of all, he said I assume for the south-oriented ones 10% soiling, which is quite, I don't know. It's a little bit too much to be honest. And the second thing is, he didn't write this in his paper, but talking to him, he said, I assume a ground cover ratio of 50% for the monocrystalline in order to prevent self-shading. But if you have only 50% ground cover ratio, you are not competitive, for instance, to a east-west oriented system with ground cover ratio close to 100%. So I think, but interestingly, what we had we made measurements on this, and what comes out is for overcasted days, we have seen even an increase of the energy yield for some days which are overcasted using these kind of reflecting structures. Compared to monocrystalline system without self-shading. So even if we do not count on the area, but only looking at the kilowatt hours output per watt peak, there was a higher energy outcome for this kind of structure. This is kind of interesting, and interestingly, there is also, if we have overcasted situation, there's a lack of energy in the future. So it could be could be of interest, this kind of approach. And then we've made first measurements using dynamic reflectors. Of course, it depends a little bit on the size of the reflector in comparison to the size of the system. If you have a huge roof and you put some 2-meter wall somewhere on the border, it doesn't count a lot. But if it's a smaller system and you have comparable size of your reflector, then it really makes a difference. The first measurements here in our case were that the effect was plus 30% energy yield for a certain day. So we have to analyze what would be the sizes, for what size could be interesting, and so on. But think about putting a reflector might be cheaper than installing a system. That's the idea. And now I'm coming to the next thing, which is a multiple use of land and building. We have dedicated time to develop and analyze systems where we combine green roofs with photovoltaic roofs. So what do you think? Green roofs? Why green roofs? But green roofs, they have some advantages. They have the function of a water retention. If there's a lot of rain, and then this rain, if there's no green roof, the rain just goes into the canalization, and they really have to pay in Switzerland for that kind of water. So it's a cost factor. And there's additional building isolation, cooling of the building, air humidification, and so on. So it also decreases the urban heating and an enhancement of biodiversity. So if you want to combine this, the most easiest thing is to say, okay, I have a PV system at one part of the roof, and the other part is green roof. Easy. So that will look like this. But is this the best design, is the question. So we have compared vertically installed bifacial modules and using the standard east-west ones with low tilt angles, and in our hemisphere south-oriented modules with a certain distance to prevent self-shading and to allow to grow that this green roof is growing. So one thing is difference in between all of this. If you look at the vertical one, the advantage of this one is you can put your modules as close as together as you want. You still have always the green roof. If you do this with this solution here in the middle, if you have a ground cover ratio of 100%, you don't have a green roof anymore. You have to make a decision: green roof or PV. Or here at the right one, you could accept maybe 50% ground cover ratio, maybe a little bit more. But if you go too close together, you have self-shading first of all, and second, there will be no plants anymore below the panels because they don't get light. So we were interested in thinking about, okay, what is happening if we go for a high ground cover ratio? And according to our analysis, these dense arrangements make really a lot of sense, even if you have self-shading. So you can really get close to the optimum energy yield and maintain the full area of the green roof. So this is a quite it's one good option for the combination of green roof and photovoltaics. So, and also the energy yield per area can reach comparable values of those systems using the modules which are tilted and with a 50% ground cover ratio and even a little bit more. So if you want more information, there was a publication at the EU PV last year, much more detailed than I can report now. So there's also this topic on agri-photovoltaics. It's a huge hype in Europe. For instance, Italy. In Italy, there will be no ground-mounted systems anymore, except in the combination with agriculture. So I think this is really a very important topic in Europe. And there are also solutions like from next to sun. using bifacial modules, and then there's enough space in between. And this solution, using bifacial modules, east-west oriented, has an additional advantage that you probably know. The power distribution over a day is different to compared to a south or north oriented, depending on the hemisphere. You don't have in the middle of the day your peak. You have more two peaks, one in the morning and one in the afternoon, which is, of course, if you think about the graph I've shown, that you have the peak in the middle of the day. It's let's say the prices you can get for this kind of energy in the future would be probably higher. The latest topic is controlling the power output of the day. We have seen the tracking system. I think tracking, horizontal axis tracking, could be a good used for this kind of controlling of the energy output. But I think concerning levelized cost of energy, I think they really compete with systems with very high ground coverage, which we do not see so often in the field. We often see these south, respectively north-oriented systems, but the east-west are not so common. But I think this 5B approach is really a good one, because modules are cheap, and you don't have to get the maximum out of the module at the moment. I think it's a very good approach in order to achieve low LCOE values. To summarize everything, so I really have to look at the time also. LCOE analysis help to predict future developments. However, LCOE is not alone, cannot predict the whole range of developments, especially now. PV in combination with further utilization will be important. What we have seen, LCOE is very sensitive on degradation and on the system lifetime. And I think just to remind, it was 10% efficiency gain can be lost by just 1% added degradation. And just this, what we figured out, the 6% absolute efficiency gain at same US dollar per watt peak module cost would tolerate only 0.7% higher degradation rate, which is for a 20 years lifetime, and a 30-year lifetime would be even worse. So understanding and lowering degradation should be a major task in research. So I'm coming to the acknowledgement, running. First of all, I would thank you all to giving me the opportunity here to work at SPREE in such a wonderful and friendly environment. It was really great. It is great here. Special thanks to Bram, who gave me this opportunity. I'm very grateful for that. It's really, I'm so happy to be here. Thanks also to my colleagues, Roger Hildebrand, who wrote the MATLAB program to make these simulations. This is all unpublished. My colleagues Markus Klenk and Selina Pfeiffer in Zurich, in my group. Thanks also, of course, to my school in Zurich, who supported me to make this research stay. And the research I have shown from the Zurich University of Applied Science was supported by the Swiss Federal Office of Energy under these two grants here shown. So thank you for your kind attention. If you have questions, please feel free. Maybe there's not so much time left, unfortunately. I have all the LCOE data with me, so if you want to know them, be free to ask. Yeah.
Thank you very much, Hartmut, for the great presentation. So a bit of the past, but also a lot of the present. So we have, like, I'm not sure, is there a lecture back to back? We don't know. We can go to questions, maybe. Yeah.
Thank you for your very good presentation and for the historical insight. I have two questions. The first is, seeing that stability of the mode of the systems and degradation are very huge factors that influence LCOE. What's the implication for other areas, so desert areas, for instance, or places like the Middle East, say North Africa, and just generally as global temperatures, are rising, what's the implication for LCOE? Taking this into consideration, seeing that these are very important factors that affect degradation of modules. The second question is about your reflectance, the new system that you showed. Is there a consideration for module heating with that kind of system? Because potentially you're also going to impact on the degradation of the modules and perhaps lower the LCOE.
Thank you for the good questions. First of all, the first question was related to these degradation factors for North Africa, for other climates, right? Yes. Of course, yeah. It will be, if there are effects which are, let's say, supporting degradation for instance, for tandems, especially for higher temperatures, then it will be even worse for these technologies. It's a question whether crystalline silicon, or I think there are also open questions with the new technologies. What will happen for higher temperatures? I think this is a major topic here in the group of BRAM, and I'm curious to see what the future brings. And the second question, it's of course, if you have these kind of reflectors and increasing irradiance, then the temperature will rise, and that can have an impact, of course, on the degradation. But this is, we are just thinking about, could it be a potential way of increasing the energy output? And I think, then I think the rest will come. I think it's really at the beginning of thinking about it, not in the, there will be, for the horizontal axis tracking system, we will probably have a pilot and demonstration object, but for the reflectors, it's not yet finalized.
Phil?
Hey, didn't see you.
Behind the light, yeah.
For the high ground coverage trackers, in your simulations, have you considered the case where you would have, say, a half cell module and they would actually track to shade half the module in the early morning, evening to reduce your angle of incidence in that case? Or where you actually strung it differently, where you had multiple sub-modules and you could actually have some self-shading without?
So this is a very good point. You're addressing a point which we also think is there is a developments at the moment to design the modules differently, shading tolerant modules. So the simulation software we have used, they cannot simulate nicely the partly shaded modules. So if you have partly shading, then of course you see also in the measurements a huge drop in energy output. So currently you would avoid that. But if you have only these slight tilt angles, you can really avoid it. But if you have larger angles, you can't avoid it. And the good question you said, could it still be beneficial if you use shading tolerant modules? And we will have, we currently get modules from AI Solar, and they have shading tolerant modules where really every single cell has a separate bypass diode. So just to really see what's happening there.
And maybe one final question, if you have time, Thorsten. Thorsten.
Thank you very much. That was a very enlightening talk, I have to say. And from all you're saying is degradation will be a very, very big role in the future. And there's one risk that I see with the module prices being so low now and degradation being maybe under control, maybe not under control. Wouldn't people who run solar farms or even rooftop systems say after 10 years, hey, modules are so cheap, I'm going to just put new modules on my roof. I see there another big risk, like in huge waste streams coming online and the PV industry becoming less sustainable as a result of that. Would you agree with that, or do you have some comments on that?
It's interesting. There was also a publication from Peters, forwarded from BRAM, and they really look at these kind of scenarios. But my personal view is, think about, after 10 years, you exchange your modules. Okay, maybe the module price is cheap, but the cost for exchanging the modules, the labor, this is horrifying. And then you have to adapt maybe also the whole system because you have different modules and so on. So I don't think that will be a good. I don't think that will be the case. I think we really have to get the modules in a way that they last a long time. Yeah.
Yeah, but maybe in view of time, let's thank Hartmut again for the excellent talk.
Thank you.
He's still here for another few weeks, so if you want to catch up with Hartmut, just send him an email or send me an email, then I can put you into contact.
Thank you so much.